Okay, let's unpack this. Welcome to the deep dive. Our mission today, really, is to cut through the noise. We want to get straight to the essential knowledge about um, building machine learning models and also using those pre-built AI services. And importantly, it's all based specifically on the source material you've shared with us.
That's right. So forget wading through docs or, endless articles yourself. We're here to pull out the most important bits for you. We'll look at the core steps when you're creating an ML model from the ground up, how you figure out if it's actually doing a good job.
Performance, yeah.
And then we'll pivot, look at some really powerful shortcuts, those ready-to-use AI capabilities. We'll focus particularly on what Azure offers, according to these sources.
Exactly. Think of this deep dive as your accelerated guide. We're hitting both the fundamental building blocks, the ML pipeline, and the impressive sort of off-the-shelf power of AI services.
Right.
It's all about understanding the landscape, but straightly through the lens of the info provided.
Okay, so where do we kick off? The sources, they pretty much immediately set the scene talking about the main goal,
Yeah.
building a machine learning model.
Yeah, and they give us a really concrete example straight away. It's this task of classifying individual income. Basically, you want a model that looks at data and predicts, is this person's income 50K or is it 50K, a two-class thing? And that's the specific problem, the pipeline process in the sources is set up to solve.
Right. And building that kind of model, it involves a structured sequence, a pipeline, you could call it.
Yeah, a pipeline. So the very first step the sources walk us through is getting the data and splitting it. They mention a common approach. You take your data set, divide it up, 70% for training the model.
Right.
And hold back 30% just for testing it later.
Okay, so data split. Then you move to actually training the model.
Yeah.
You use that bigger 70% chunk, the training data, and feed it into a component. This component applies a specific algorithm, a machine learning algorithm.
This is where the learning actually happens.
Exactly. This is the learning phase.
And the sources stress this point. It's crucial that you tell the model what to learn. It learns based on that income column.
Which they call the label. That's the target, the thing you want to predict.
Precisely. The label is key. So after the model's learned from that training data, the next step is scoring. Now you bring in that 30% test data you kept aside.
The unseen data.
Yeah, the unseen data. You run the model on it, see how well it predicts the income values there. It gives you a first taste of its performance.
And that scoring, it leads right into the final step they mentioned, evaluating the model. You need to systematically understand, okay, how good were those predictions on the test data? Really measure it.
Now, when we talk about building a pipeline like this, what kind of prediction task are we actually doing? The sources give a quick rundown of the main types of ML problems these algorithms tackle. Right. There's classification. That's all about putting data into boxes, into categories. Our income example, that's a two-class or binary classification. Is it A or B? The source also gives another example. Is a user going to buy this product? Yes or no? Simple. But you can also have multi-class, where there are lots of possible categories.
Okay. Then you've got regression.
Yes.
So here, the goal isn't categories. It's predicting a number, a continuous value, usually based on past data. The example they give is forecasting sales for next month. You're predicting actual dollar amounts or unit counts.
Numbers, not labels. Got it.
Yeah. And finally, clustering. This one's a bit different. It's about grouping similar data points together without knowing the categories beforehand. The source suggests maybe segmenting customers into different groups for a loyalty program or something, finding natural groupings.
Okay, that makes sense. So if we circle back to our income example in the training, the sources highlight this core idea, supervised learning.
Right, supervised learning.
And in supervised learning, your data set has both features, which is the input data, right? Like age, job, hours, worked for the income thing.
The descriptors.
And it has the label, the correct answer you want the model to learn, the actual income bracket in this case.
Exactly. Features in, label prediction out. That's the supervised idea. And the sources also, they briefly touch on feature selection, which is basically picking the most useful features from all the data you have. And feature engineering, where you might, say, create new features from existing ones to maybe help the model learn better.
So preparing the data before you even train. Important stuff.
Critical steps, yeah. Often takes a lot of the time.
Okay, so you've trained it, you've scored it. But how do you really know if it's any good? This is where evaluation comes in, and the sources lay out different metrics depending on the job classification or regression.
Right, let's start with classification models. The sources list a few metrics. They mention accuracy. The definition in the source, proportion of true results over positive results, is Well, maybe a bit confusingly worded.
Yeah, I read that.
More typically, you think of accuracy as just. What percentage of predictions did the model get right overall, out of
Okay,
everything?
simple percentage correct. That's clearer. Then there's precision and recall.
Yes. Precision, the source says, relates to the fraction of the total amount of relevant cases that were actually retrieved. Let's try to simplify that. Think of all the times your model said something was positive, like predicted 50K income. How often was it actually right?
So it's about not crying wolf, avoiding false positive.
Exactly. Precision is about the accuracy of your positive predictions. And recall. Now, the source description here is also tangled with F1 scores, but recall is really about finding all the actual positive cases. So out of everyone who actually earns over 50K, how many did your model correctly spot?
So finding the needles in the haystack, avoiding false negatives.
You got it.
Work.
Making sure you don't miss the things you're looking for.
Okay, precision recall. And the F1 score. The source calls it a weighted average.
Yeah, the F1 score is basically a way to combine precision and recall into one number. It gives you a balance. Sometimes you care more about precision, sometimes recall. F1 tries to balance both. The source notes an ideal score is 1, perfect balance.
One number to rule them. Well, to balance them.
Sort of. And lastly, for classification, there's AUC area under the curve. This one's a bit more technical, but it basically shows how well the model can tell the difference between the positive and negative classes across various thresholds. Higher AUC, closer to 1, generally means better separation.
Okay, good indicator. Now what about regression, predicting numbers? The sources say the goal here is measuring how close the predictions are to the outcomes, and lower scores are better.
Exactly. For regression, you want the error to be small. Lower is better. The sources list mean absolute error, or MAE. That's just the average size of your errors, ignoring if they were too high or too low, just the average distance.
Okay, average error magnitude.
Then root mean squared error, RMSE. Similar idea, but it squares the errors before averaging. This means it penalizes bigger mistakes more heavily than MAE does.
Right, so big misses hurt your RMSE score more.
Precisely. They also mention relative absolute error, RAE, and relative square error, RSE. These are basically normalized versions of MAE and RMSE.
Okay.
Makes it easier to compare error across maybe different models or data sets.
Normalized, okay.
And finally, the coefficient of determination, often called R squared. This tells you how much of the variation in the thing you're predicting, like sales, can be explained by your model's inputs. The source says it's between 0 and 1. Higher means your model explains more variance, so it has better predictive power.
Phew. Okay, that is a lot of ways to measure. So let's say you've done all that. Built it, trained it, scored it, evaluated it, you're happy, now you want to actually use it. The sources say to consume the pipeline, you first have to deploy it.
That's the term, yeah, deploy it. And you've got options like set it up for real-time predictions, it's an inference pipeline, or maybe process big chunks of data periodically, a batch pipeline.
Okay, depends on the need. And once it's ready.
Make it available, you put an endpoint in place. The source gives Azure Kubernetes Service, AKS, as an example compute solution to deploy to. That's common for production because, it handles scaling and reliability pretty well.
AKS.
And with that endpoint live, your application can just send data to it usually via a web request, a REST endpoint.
Like calling a website API.
Exactly like that.
Yeah.
And get predictions back, usually secured with some kind of authentication key, of course.
Okay, that covers the build-it-yourself pipeline, soup to nuts. But then the sources introduce this big time saver, automated machine learning, AutoML.
Yeah, this is pretty cool. Instead of you picking the algorithm and tuning everything, AutoML does a lot of that heavy lifting. It automatically tries out multiple models for you, uses different algorithms, different settings.
So it runs experiments automatically.
Basically, yeah.
Yeah.
It builds and tests a whole bunch of different pipelines on your data, looking for the one that performs best according to the metrics you care about.
That sounds powerful. What do you need to give it?
You still need your labeled training data, obviously. You need that to learn. But the key thing the sources emphasize is you don't necessarily need deep programming or ML expertise to get started with it.
Lowering the barrier to entry.
Definitely. It can massively speed up that experimentation phase.
Okay, that's a great shortcut for building your own model. But then the sources shift gears again, right? Moving away from building models, even with AutoML's help, to just using AI features that are already built, ready to go. The pre-built AI services, specifically in Azure.
Exactly. This is a different philosophy. The core idea is add smart features to your app without building the underlying ML yourself. The source has that image upload example. You need tags or object detection for user photos. Don't build an image recognition model. Just call an Azure service that does it.
Plug and play AI almost.
Pretty much.
Yeah.
And the sources clarify how you manage these. You can set up a resource for just one service, like Azure AI Vision, if that's all you need, and maybe you want to track its costs separately. Or if you think you'll use a few different things, Vision, Language, maybe others, you can get a combined Azure AI services resource. Manage them together.
Flexibility there. So what are some of these specific powerful services the sources detail? What can they actually do?
Okay, let's run through them. For images and video, there's Azure AI Vision. The sources list things like image analysis that's getting tags, descriptions, finding objects, optical character recognition, OCR, pulling text out of images,
Reading text and pictures, yeah.
and a face API specifically for working with human faces, detection analysis.
Right, and you mentioned the face service too. Is that part of Vision or separate?
It's often grouped under the AI Vision umbrella, or sometimes considered alongside it. It's really specialized for faces. So the Detect API finds faces, gives you the box around them, maybe attributes like glasses or masks. Then there's face recognition. You can build a group of known people, a person group, and see if a new face matches anyone in your group.
Identifying people you've already registered.
Exactly. And a Verify API too, just to check if, say, this face image matches this specific known person, a one-to-one check.
Okay, very specific face tasks. Now, what if the general image stuff isn't quite right for my specific pictures? Like I have unique items I need to identify.
Good question. That's where custom vision comes in. Its whole purpose, according to the sources, is letting you build and deploy your own image identification models using your labels for your specific items.
So I train it myself.
Yep. You provide your own images, you label them. You can do this through a web portal or use SDKs, APIs. And the sources mention two main project types. Image classification.
Yeah.
You assign labels to the whole image, like is this picture indoors or outdoors, or does it contain a dog? It can be one label or multiple.
Okay, classifying the whole scene.
Right. Or object detection. This goes further. It finds the specific things within the image that you've labeled, draws boxes around them, and tells you where they are.
Finding and locating my custom objects.
Cool. Okay, moving from pictures to paper. Documents. Documents, yeah. That's document intelligence. Used to be called form recognizer. It's all about pulling data out of forms and documents automatically.
Like invoices.
Invoices are a prime example. The sources mention a pre-built invoice model. You feed it an invoice image or PDF. It pulls out the vendor name, total amount, line items, dates, structured data. But crucially, you can also train custom models. If you have unique forms or documents, you can teach it to extract the specific fields you care about.
Very useful for automating paperwork. Okay, last big category, text. What about understanding language?
For that, the sources point to the Azure AI Language service. It's like a toolkit for text analysis. Key features mentioned. Named Entity Recognition, or NER. This finds and categorizes things in text people's names, locations, organizations, dates, events.
Picking out the important nouns and concepts.
Exactly. There's language detection, figures out what language the text is in. Supports over 100, apparently. Sentiment analysis is the text positive, negative, neutral. Often gives a confidence score, too.
Useful for customer feedback, maybe.
Definitely. Then key phrase extraction pulls out the main topics or talking points, like a summary of keywords. And a really powerful one, custom question answering.
What's that do?
It lets you build like a natural language interface over your own information. Think FAQs, manuals, knowledge bases. You feed that static info in, create a knowledge base.
Right.
And then users can ask questions in plain English, and the service finds the answer from your content. Great for building chatbots or internal help systems.
Wow. Okay, so that's quite a range of pre-built capabilities.
It really is. So if we just take a step back, this whole deep dive, what's the journey been? We started with the nuts and bolts, right? Building an ML pipeline step by step, getting data, splitting it, trading on labels, and then really digging into evaluation, those metrics for classification regression.
Yeah, understanding how to measure success. And then we saw AutoML as a way to speed up that building process, automating the experiment.
Right, a significant shortcut. But then we shifted completely to leveraging these pre-built Azure AI services, tools designed for very specific, often complex tasks that you can just call. Understanding images, analyzing faces, reading documents, getting insights from text.
It feels like two different worlds almost, building versus using.
In a way. And understanding both sides, how custom models are built and evaluated, and what these powerful specialized ready-made tools can do. That really gives you, the listener, a clearer map of the AI landscape, doesn't it? helps you focus on what you need to know quickly, which was the goal based on our sources.
Absolutely. It clarifies the options.
So here's something to chew on, maybe. Based on everything we've unpacked from these sources, think about the effort involved in meticulously building and tuning that custom income classification model we started with, versus the sheer range of complex tasks handled almost instantly by these pre-built services, analyzing sentiment, finding faces, pulling data from an invoice. What does that suggest about where the leverage might be today when you're trying to apply AI? Is it mostly about becoming a deep expert in building one specific type of model? Or is the real power perhaps in getting skilled at identifying and creatively combining these different specialized AI tools to solve bigger problems?